we now know that we have a means of differencing a discrete sequence, we have a means of carrying out a running sum of a discrete sequence, we can differentiate a continuous time function, we can running integrate a continuous time function, we can do all these things. Suppose without regard or prejudice to the manner in which these circuits are constructed which can do these calculations, suppose we merely represent them by a block. Suppose we say that we can have a system which takes a continuous time signal x t and yields at the output dxt by dt, or we had a similar discrete system which took in x n as the input and generated at the output its first difference x n minus x n minus 1. We would replace both we would represent both these by d and d. The context would make it very clear whether we are concerned with a discrete system or a continuous time system. Okay. Similarly, we could have a running integrator or a running summer. X t goes inside and what you get at the output is integral minus infinity to t x t dash dt dash. Fine. Here you would have this, we would denote by this symbol, and this we would denote by this symbol over here. It would be the running summer x n would yield summation minus infinity k equals minus infinity to n x n minus k. Suppose we have these blocks. Let us construct some more blocks. Let us have a summing block. This block takes two inputs, let us say x 1 n or x 1 t, does not matter, the symbolism is the same, x 2 n, and the output it produces is x 1 n plus x 2 n. This is what we would call a summing block. We could also have a special block for a system which merely multiplies by a scalar constant. We call that an amplifier in conventional electrical engineering. So, we could have an amplifier. Which takes a sequence x t or x n as the input, this depending upon whether it is discrete or continuous, and produces as the output, let us say if this has a gain of alpha, you would get alpha x t or alpha x n as the output. So, these are the four kinds of blocks that will constitute the objects of our next discussion. Our next discussion will be to actually build systems which can solve differential equations or difference equations. Suppose we want to solve the difference equation that we have been playing around with till recently. Suppose we have let us say an even simpler system. Suppose we just had x n plus beta x n minus 1 equals y n. Can we build an interconnection of these elementary blocks that we have over here to get y n if we have the sequence xn supplied to us. That is not very hard. Let xn be available over here. We need to add xn to something, namely to this term. Let us do that by constructing a summing block. Fine. Now, what is the other thing that we need to add to it? What we need to add to it is beta times x n minus 1, but we do not have x n minus 1 available right now. We will have to make it by taking x n out of here, putting it in a D block, fine, so that what you get here is x n minus 1. Now, this is only x n minus 1, we want beta x n minus 1. So, what we do is to append another amplifier block with a gain of beta, and this now is beta x n minus 1. So, you have x n coming from this side, beta x n minus 1 coming from this side, and you now add the two, and what you get here would actually be y n. Fine. This is a very simple kind of filter which just takes the present value of x n and a certain scaled value of the previous x n, that is x n minus 1, and adds them to yield the current value of y n. In short, y n is said to be the moving average of x n. This is called a moving average filter. It essentially creates a gradually moving average. At every instant of time, the window over which the input sequence is being averaged is being shifted by one position. So, you get this moving average filter. More precisely, this is called a first order moving average filter. If you want to know why, the fact is that the order of a moving average filter, which we will simply call an MA filter, is decided by the number of delays or D blocks that it contains. In this case, it contains only one, so it is a first order filter. If you wish to generalize this to a second order filter, all you would have is an additional D block and therefore, a second delayed version of x n, namely x n minus 2, which would also be scaled by some factor and would get added to x n and a scaled version of x n minus 1 and so on to get y n. So, let us write the equation for this. I will not draw the block diagram of this, instead I will go ahead and define the nth order moving average filters or the mth order moving average filter directly. if you wish to see how this is implemented, well, there is a naive way of implementing it and there is a slightly smarter way of implementing it. We will apply the naive approach for a second order implementation, that is to say for a second order filter m equal to 2, and then we will see how we can make it slightly smarter. We have x n as before, and we need both x n minus 1 and x n minus 2. So, one way would be to take x n minus 1 or to take x n and delay it by 1 unit of time to get x n minus 1. This x n minus 1 would then be scaled by b1, x n itself would be scaled by b0 according to the equation, and you also need x n minus 2. So, you could start with x n right away, put one delay over here and yet another delay over here, and get x n minus 2, to which you would attach the appropriate scale factor b2. Now that you have all these, you could take a summing block over here, add this, and add this, and all this together would give you y n. Now, this kind of a diagram is ripe for just a few very straightforward simplifications. First of all, let us say that we want to keep the number of blocks of whatever kind to the minimum, be they delay blocks or gain blocks such as b0, b1, b2, or the summing blocks that we have over here. In the case of the summing block, which is the circle with the plus inside, we want to ensure that no summing block is at any time involved with summing more than two numbers, two quantities, two functions, whatever. So, keeping these constraints in mind, we can make a simplified version of this diagram, which does, however, exactly the same job, and that's as follows. Now, we have the three delayed and appropriately scaled versions of x n: x n times b naught, x n minus 1 times b 1, and x n minus 2 times b 2. With these, we now add these two at a time. First, we add x n minus 2 b 2 and x n minus 1 b 1 to get this. To this sum, in turn, we add b0 x n to get this, and this of course is now y n. The second block is much more regular in appearance, has one delay block less, and has two summing blocks instead of one, but each summing block has only two inputs and one output. So, this is the more standardized form of a second order moving average filter, which could easily be generalized in a manner that I am about to proceed to do. All you do to generalize this further is to have n delays instead of just 2, so that you go on like this. Here of course, you will have b2, and you will add this through another summing block. You go down like this and you have the last delay, and the output of this delay would be x n minus capital M. This would go to be M and would go to a summing block which adds it to the previous one. This now is an mth order moving average filter. Right. Now, you see moving average filters, while they are nice to look at, are not really any related to our differential equations. In short, they are a different class altogether, and their general form is summarized by the expression that we had earlier over here in this page, namely this. This is the general form of the mth order moving average filter. Of the discrete kind, of course, we are now presently involved in only discussions about discrete systems. Moving average filters always have a finite impulse response. That is because the moving average filter simply sums up certain previous values of x n with appropriate scales. That is all it does, and the number of previous values of x n that are added is simply capital M. That many previous values of x n are being added together. That is why the impulse response of this is very, very easily calculated. H n, which is equal to y n when x n equals delta n, is given by, you just have to substitute delta n for x n on the right side, k equals 0 to m b k delta n minus k. This is the impulse response, as simple as that, and therefore, it will have only capital M different non-zero points in the impulse response. Actually m plus 1, because even at m equal to 0 you have, so it is m plus 1. At most. It could have less than m non-zero values if any of the bk's is 0 for k less than m. Then it would still be called an mth order filter, because there are m delays in the circuit, m delay blocks in the circuit in the diagram. But it would have, it could have a smaller number of non-zero values. All right. Next, suppose we want to solve differential equations like we hoped we would be able to, or as we are now concerned with difference equations if we wish to solve them. Let us see how we can solve a difference equation of the simplest kind, that is the study of what are called autoregressive filters. autoregressive filters are genuinely different from moving average filters. Moving average filters, as I said, have only a finite impulse response in this sense that they have only finitely many non-zero values in the impulse response. That is why they are also called FIR filters, finite impulse response filters. The autoregressive filters, as it turns out, will have an infinite number of non-zero values in the impulse response. An autoregressive filter, the simplest case of which would be a first order differential equation, first order difference equation, would be as follows. An example, yn plus say a y n minus 1 equals x n. So, here we have not past values of x n involved in the computation, at least not explicitly so, but certainly past values of y n involved in this computation. Now, one way to approach this problem would be to go along the lines that we followed when we tried to find the impulse response of a first order a system described by an equation such as this. That was there in some previous slide a little while ago. Let us just take a look. Yes, here is an example. There must be more examples if we go further back. Yeah, here is here is the other example. This one is the causal version, causal solution. And the next was the anti-causal solution. Fine. Now, for that causal solution or for that anti-causal solution, you have Hn, sorry, here it should not be x, it should be delta. There is a mistake in my previous slide over here. This should be delta over here, and likewise let us go to the previous one and see what we have done. Hn equals this, yeah, this is okay. So, we could keep recursively using older and older values of xn and not using the past values of yn. But as you saw in the process by which we obtained the impulse response of solutions for causal and non-causal anti-causal solutions for difference equations, you still require some one past value of yn. So, the naive way of going about solving an equation such as this would be to express yn in terms of yn minus 1 and xn, and then yn minus 1 in terms of xn minus 1 and xn and yn minus 2 and so on. So, if we keep doing this, we will get an expression for yn that involves an infinite number of terms such as these, such as this expression. This has an infinite number of terms because k equals 1 to infinity, it goes from 1 to infinity. This also has an infinite number of terms. Fine. Now, this is not convenient. If it has an infinite number of terms, that means it requires an infinite number of delay blocks, D blocks. In that very clumsy sense of the term, any autoregressive filter would be an infinite order filter, but that is not how we are going to look at an autoregressive filter. We are not going to treat it as some kind of a distorted or mutated FIR filter with an infinite number of delay elements. There is a much nicer and simpler way of doing it, but in order to understand this, one has to temporarily live with a paradox. What I am going to assume in this case, well, let me first rearrange the equation. so that it is in the convenient form of yn equal to something. So, you can write this as yn equals xn minus a y n minus 1. Suppose this is the equation you have, then what is the best way of implementing this? You need to know yn, right? You have to compute yn, but unfortunately to compute yn you need to know both xn as well as yn minus 1. A is known. Now, so you need yn minus 1 to find out yn, all right, but yn minus 1 is not known either. Yn minus 1 is xn minus 1 minus a yn minus 2. So, you would have to know yn minus 2. So, you will have to keep going further and further back, because there is always one term of yn which you do not know, such as yn minus 2 or yn minus 3 or yn minus 4. The problem only goes further and further away, but it does not go away altogether. So, what is the solution? The solution is to pretend temporarily that you have somehow solved this equation and have actually evaluated yn. Suppose you make that temporary hypothetical belief assumption that yn has somehow been found. Now, if yn has been found, then you know the value of the sequence y for the point n, for the point n minus 1 and n minus 2 and everything. Only then you will say that you know the entire sequence n. So, well, take this and put a delay on it. The sequence that appears at this point will be y n minus 1. This of course is a delay block, as I said. It is a delay block. Now that you have yn minus 1, let us try to proceed. Remember, this entire thing is founded on the belief that we have yn somehow, and we will just have to live with that belief for a little longer. And since we have yn minus 1 now, we will make the appropriately scaled version of yn minus 1, which is minus a. So, what you have here is minus a y n minus 1. So, if you have minus a y n minus 1 and you have x n, all you have to do is to add these two, and the sum will itself be equal to y n. So, all I do is put up a summing block like this and let x n go into it and minus a y n minus 1 go into it. What should I get over here? According to the equation, I should get y n over here, and well, though I got y n assuming that I already had it, I am happy to see that I do have it. So, I just go ahead and connect these 2 points. So, it produces y n and feeds upon itself to produce y n continually in future, in perpetuity. This is how a first order autoregressive filter functions. You are able to get y n if you start by pretending that you have y n. A second order autoregressive filter will be one which can solve a second order difference equation. Second order difference equation would be of the form, let me put it in the more general form with all kinds of coefficients in it. Summation k equals 0 to 2 in this case, a k y n minus k equals x n. You just have to extend the previous model a little further and write y n equals 1 by A0 1 by A0 times xn minus A1 y n minus 1 minus A2 y n minus 2. This would give me y n. Now, this also can be implemented if you follow the same trick that you followed a little while ago, which is to pretend that you have y n. Then you put one delay on this and get y n minus 1, put another delay on it and get y n minus 2. So, you have these, all this hypothetical for the time being because y n itself is not known. But now that you have these, you are in a position to put in some of these coefficients. This will be minus A2, this will be minus A1, and you have to add all these things. So, you put a summing point over here. Okay. Now, you have these two things. These two things plus xn xn complete the picture in some sense. Xn plus minus A1 times yn minus 1 plus minus A2 times yn minus 2. What is all this equal to? This is just A naught times yn, but we do not want A naught yn, we want yn. So, we just now here put a forward looking scaling block and write here A naught to the power minus 1, that is 1 by A naught. This what do you find at this point? You just find yn. So, you have got yn once again. The more general equation for the nth order autoregressive filter, which we just write as AR, filter, is found by just generalizing this diagram a little bit, which I will do without rewriting it all over again. I have this already. So, I will put another delay block over here. So, I will get yn minus 3 and so on dot dot until I come to the last delay block, before which I have yn minus n plus 1, and with this delay finally you get yn minus n, and you take this and scale it with minus A capital N. This will be minus A capital M minus 1 N minus 1 minus A n minus A n minus 1, and then you add all these using the tricks for shortcuts that we are already familiar with. So, this is it. You now have an nth order autoregressive filter which will give the output yn if you have xn and these many delays, scale multiplier scalars like A0 inverse A1 and A2, minus A1, minus A2 and so on until the last term, which was minus An. This gives you an nth order AR filter. Now, see the point with an AR filter, it does not even have to be nth order, even the first order AR filter is full of surprises. What we want to see is whether its impulse response is really infinite. It is not hard to see. Suppose you apply xn as just delta n, then what would happen in a system like this? Delta n would add to something and come over here, and a delayed delta n would be delta n minus 1. It would get scaled and it would come back here. And even though input is no longer being given, this would now act as the input. Delta n, or rather minus a1 minus a delta n would appear as the next output, and this would go on and on, on and on, on and on, so that you would get an infinite impulse response, an impulse response with a support that is infinite. So, these filters are called IIR filters. All AR filters are called IIR filters because their impulse response goes on forever. That is why it is called an infinite impulse response filter or IIR filter. Now, you could in principle have a filter which contains both FIR and IIR elements. It would of course jointly be IIR only, it would not be FIR under any circumstances, but we will see how one can combine these two and make a block diagram for a more general filter which contains both an IIR and an FIR component. So, let us look at the equation of a system which contains both IIR and FIR components. Such a system would have a general expression like this. On the left side, we would have the part that is a difference equation, that is like the left side of a difference equation. K equals 0 to capital N A k y n minus k, and this would be equal to a similar sum, weighted sum of past values and the present value of x n. That is to say, k equals 0 to m b k x n minus k is what you have on the right side. So, all right, suppose you have this, then m in general could be different from n, but it would be convenient for us to keep both numbers the same, and in order to keep both numbers the same, there is a very simple trick one can use. The trick one uses is to choose the larger of m and n, that is to say max m n. Choose the larger of the two and call it n. Then we rewrite the equation so that there are exactly n terms on either side. Now, the extra terms that need to be added on the side that was earlier possessed of a smaller number of terms will essentially be terms where the coefficients are 0. Fine. So, suppose n were equal to 5 and m were equal to 3. Then since n is equal to 5, I would have a5 not equal to 0, and I cannot comment on a4 to a0, some of those terms might possibly be 0. On the other hand, for the right side, since m is equal to 3, we can write that b3 is not equal to 0, right. There is no higher coefficient on the right side than b3 because capital M equals 3. But that does not stop us from simply saying that b4 equals b5 equals 0. Thus, we would write summation. Keeping this in mind, we would write summation ak y n minus k equals 0 to n, which is equal to 5, equals k equals 0 to m plus 2 bk x n minus k. Now, since n equals m plus 2, we can call both of them n and simply write summation k equals 0 to n ak y n minus k equals k equals 0 to n bk x n minus k, keeping in mind that this is true, right. So, we now have a more convenient form of this kind of an equation which we want to solve to find y n given x n. So, how do we do it? We have to rewrite this equation so that we have an explicit expression for y n, and that is not hard to do. We can write y n equals 1 by a naught, which is the coefficient of y n, times bk summation k equals 0 to capital N x n minus k minus ak summation k equals 1 to n y n minus k. Note that the y n minus 0 term is not incorporated on the right side, but on the left side, namely y n itself. All other terms of the left hand side have been pushed to the right, so that you now have an explicit expression for y n. With this explicit expression, we can see how this thing can be constructed. You have 1 by a 0 into b, bk summation, sorry, there is a mistake here. This should be over here. This also should be over here. Let us just erase this and make it more spacious. This is the correct expression. Sorry for the mistake. Now, how do we implement this? We look at these two blocks as two separate blocks and try to find these two intermediate quantities, the result of the summation of all the terms in the first summation and the result of the second summation. To get the first summation, we already have a certain mechanism, namely we take x n and delay it a sufficient number of times to get the different delayed versions of the signal. So, you have here x n minus m, here you have x n. So, you multiply all these by respective scales b 0 and this will be b m. Fine. Now, let us add all these things up. B1 adding up over here, there is another summer over here and so on till you have a summation over here which gets an input from Bm x n minus m. So, you have all these things. This is the summation of the first set of terms. Now, we need the second set of terms. After we add these two, there is still a little more work to be done, but let us construct the second set of terms. The second set of terms, if you look back, has y n minus k starting from k equal to 1 to k equals capital N. So, you have various delayed versions of y n starting with delay by 1, delay by 2 and so on. So, now I will assume that y n is available over here, the same trick that I played before. Y n is available here. So, now if I put a delay over here, you find that y n minus 1 is available and so on ad infinitum. So, you get a further delay and here you get y n minus n. That is what we have over here. Now, let us scale all each of these terms by the appropriate scale factor. Y n minus n gets scaled by a n minus a n actually, and y so on up to here where y n minus 1 is getting scaled by minus a 1. Let us now add all these terms together separately like we are about to do. So, we have added all the terms in the second summation, we have added all the terms in the first summation. Now, we have to put all these together. Now, how do we put them together? Not hard. You have got all these terms in the sum over here. You put another summing block over here and you now have a0 y n. So, in order to get all this to evaluate to y n, you just now multiply by 1 by a0. So, what you have is 1 by a0 y n and that when added to this or rather when connected to this will give you y n. This is a completely self consistent set of blocks, arranged set of blocks which will generate y n, the solution to the differential equation which had x n as the input. Alright. Now, we have this. You see, each of these blocks is essentially implementing some kind of a convolution because it is a linear time invariant block having constants at all these summation points before all these summation points which are scaling the original signal and then we are adding up. So, we are just generating a linear function or a quantity which is linearly related to x n. Okay. Now, keeping this in mind, what can we do? Because this whole thing is linear, let me say that this block has an impulse response which is something I will call h1 of n. Likewise, this will have an impulse response which I will call h2 of n. Now, h1 of n is FIR, as you know. h2 of n is IIR. Okay. More importantly, since these two diagrams have a lot in common, we can rearrange these two diagrams. But before we rearrange, we should be very clear about not just the fact that this is FIR and this is IIR, but the fact that this block is essentially implementing a linear time invariant system and therefore can be equivalent to the computation of convolution. In short, if this is what we call h1n and this is what we call xn, what signal do we have at this point? The answer we have is that is xn convolved with h1 of n. That is what you get over here. Now, this is another block which is also linear time invariant, and this block is now processing this signal and producing yn. In short, I can express yn also as a convolution of h2n and the input to the second block. Therefore, I can write yn equals xn convolved with hn. Okay. This in turn convolved with, this was h1n, this in turn convolved with h2n. This is a total convolution of the FIR part followed by the IIR part with the input signal to get yn, the output sequence. An important thing that we can now do is remember that convolution is commutative. So, we can as well write yn as equal to xn first convolved with h1 n and then convolved with h2 n. Sorry, this is what we had already done. What we want is to reverse the order of the two convolutions and write h2n over here and write h1n over here. What does this serve? What help does this give us? What do we get out of doing this? That is what we will now see. I have a block over here and I have a second block over here. This is h1 and this is h2. We are now going to exchange their positions. You apply xn and now you have to process xn with the h2 block first, and the h2 block consisted of a summation okay, and here you had A0 inverse. Here after this was actually some output. From here you had a delay and so on until you had the last delay over here. We had a set of delays. Now, this delay was scaled by a, or rather minus a n this similarly would be scaled by minus A1, and this would get into this and so on. This is just the same block that we had before, except that now the input is xn and the output is something that we can call, say, un or wn, still better. Now wn is xn convolved with h2n. What do we do with wn? We now put the moving average part, the FIR part, on this side, so that we take this over like this and scale it by B0, take it down through a delay and scale this by B1, take it further down until you finally get Bn. Now remember that the number of coefficients in both is same, in both sides are same, for both the set of terms is same, except that we are always free to assume as per convenient to us whether some of the higher end Bn's are 0 or some of the higher end An's are 0. So now we have this, and then again construct the intermediate sums. And get, since we have just exchanged the blocks, the final result of all this must still be yn, which indeed it is. So you have yn over there. But now let us look at these blocks. You have something called wn over here, and wn has been delayed n different times for the moving average part and n different times for the autoregressive part, but it is the same signal which is getting delayed 2 times through 2 sets of parallel delay blocks. We need only one set of parallel delay blocks. So we could actually simplify this diagram by combining all these delays together. If this is wn, this will be w dash n, but w dash n is required for this as well, and so on until here you will get w delayed by n. You do not get w dash n over here. What you would get is w n minus 1, which is required by both sides, and finally here you would get w n minus n. That is what you would get over here, correct. So let us just knock off 2 parallel sets of delay blocks and replace it by one set of delay blocks. So I am going to do that by removing these parts and putting a single signal which directly goes in over here. This gets delayed by 1 time. This is wn actually, and this goes to both sides, so on until you finally have again a delay. One input going over here and of course the other input going over here. This is a further simplification of making block diagrams for systems described by differential equations, the general systems that we had, autoregressive as well as moving average systems. So this is the general block diagram. This is called a direct form 2 implementation. And the implementation we had before, where you had 2 sets of blocks, 2 complete independent set of delays, etc., is called a direct form 1. realization. So, which is better? Direct form 2 is definitely better because it does the same job as direct form 1, but it does it using half the number of delays that the direct form 1 used.